All right, guys, last video for nuclear chemistry. And today we're going to talk about half-life, which is it's the time it takes. It's an amount of time. Nope, 10. For half of a radioactive sample to decay, meaning like turn into something else, emit particles. Like if I have 100 grams of something, how long will it take for it to be only 50 grams left? Okay. Does half-life ever change? Never. If we go back to table N, I'll scroll back so that you guys can see it. Ah, I underestimated how far back it was. Here it is. Okay, so if we look at table N, we know that this table gives us the decay mode, the particle that the atom releases to get more stable. It also gives us the half-life. Notice that different radioisotopes have very different half-lives. Look at the units. We have from milliseconds all the way to years. So certain things decay a lot quicker than others. And notice that each one has its own. So like for example, iodine 131, it's always going to take 8 days for half of it to decay. It doesn't matter on temperature or any other thing they could ask you about. It never ever changes. It just depends on what the element is, and that's going to be its half-life. Okay, where am I? Okay, so here we go. So iodine 131, we're going to talk in a little bit about the uses of these radioisotopes, some of them, but iodine 131 is something that they actually use on people to take a look at thyroids. So it's something that takes 8 days for half of it to disappear, which if you look at that chart in the grand scheme of things, that's not very long. And that's a good thing because if we're injected with something radioactive, we want that to leave our bodies as quickly as possible. But let's take a look at an example question. This is something that you guys will have to be able to do. So they're telling us that we had 100 grams of uranium. So I'm going to put that right here. I'm sorry, 100 grams of iodine, and that they want to know how much of that iodine is still going to be left after 32 days. So if 32 days total went by, and I know that one half-life is 8 days, if I divide those two numbers, I can figure out how many half-lives went by, which is you figuring out how many times that mass was cut in half. So when no time went by, I had 100 grams of my sample. I know that this iodine underwent 4 half-lives. So after 8 days went by, one half-life, my mass gets cut in half. When another 8 days go by, so now 16 days have gone by total, I got cut in half again. When another 8 days go by, 24 days total, I got 12.5 grams left. And when my 32 days go by, my 4 half-lives, I have only 6.25 grams left. Okay, so half-life, these are problems that you guys are going to have to solve. And they basically mean you have to like set up a little chart. When they say how much, they could mean mass or they could mean fraction. And this fraction column is pretty easy. I want you guys to think about a pizza, right? A pizza is cut into 8 slices. If no time has gone by, I have 8 out of 8 slices left as a fraction. If you see 8 over 8, how can you write that as a fraction? You can reduce that to 1. So anytime no time has gone by, your fraction column should have a 1 in it. You have the whole amount. Now, as you cut that in half, you're just going to write it as a fraction. So what's 1 cut in half? A half. What's a half cut in half? A fourth. What's a fourth cut in half? An eighth. What's an eighth cut in half? 1/16. So if they asked you about a fraction, after 4 half-lives, after 32 days, only 1/16 of the original iodine would remain. Um, the lowest I've seen them go, guys, as far as like fractions go, this would turn into 1/32 if 5 half-lives went by. Okay. But this question is asking about 32 days, so you would want to pick one of these as your answer. Okay. All right. So this is just a graph showing half-life, and to show you that decay is exponential. At first, when you have a really large amount of the substance, when you cut that in half, that's going to be a big difference, a big drop. But as time goes by, your amount of radioactive substance is smaller. So when you cut that in half, your change is going to be smaller. Eventually, we're going to get to a point where we're very close to zero, but you're just going to be cutting that number in half. It's going to be very hard to get to a point where there's 0 grams of that radioactive substance left. Is it going to be ridiculously small, the amount? Yes, but very hard to get down to 0 as far as radioactivity goes. You could also use this graph, like if it was a substance and you didn't know what it was, therefore you couldn't look up its half-life on table N, you can use the graph to figure out what the half-life is. So I would say for strontium 90, I started with 10 grams of it. So half would be about 5 grams. So I would say, all right, well, here's my half-life. Little less than 30 years would be my half-life. So you can use this graph in that way too. Okay, so here are my half-life problems. When you can, you want to use table N, because that's going to help you figure out for those known substances how many half-lives went by. So let's look at the first one. This is your easiest kind of question, where they give you a radioisotope that's on table N, and they tell you how much you started with, and they want to know how much you're going to end with after a certain amount of time. So now 57.12 days went by. Can you guys go to table N, and I want you to look up what the half-life of P32 is. Okay, and when you get there, you should see that one half-life is 14.28 days. So again, guys, just like I did before, if I divide, I'm going to be able to calculate how many half-lives went by. All right, so now here is where you have to set up your chart. I always want you to have a half-life column. That's important. The other column depends on what they're asking you, either like the mass or the fraction. This question is specifically asking us about a fraction, so that's what I want to title this column. It literally doesn't matter that they told me I started with 80 grams, because they only want to know what fraction of my original is going to be left. Okay? Very, very important. Half-life column always needs to start with 0. The original mass they give you is for no time going by. Then you want to number from 1 to, I'll number to 4 here because I know that 4 half-lives went by. All right, my fraction column always starts with 1. At time 0, I have my full amount. Every time I jump down 1, I want to cut in half. And when I get down to 4, I realize that I will have 1/16 of my substance left. So every time you jump down 1, you're cutting in half. Okay, let's look at number 2. So my second one, guys, is they're telling me how much I ended with, and they want to know what my original amount is going to be. Very, very similar process to the one that we just did. All right, so they're not telling me what my sample is, but they're telling me how much time went by, and they're telling me what the half-life is. So this is nice and easy. I don't have to go to table N. So if I know how much total time went by, and I know what one half-life is, I can figure out that 2 half-lives went by. So again, I'm in a position where I can set up a chart. half-life. Now they seem to be they gave me mass here. The question doesn't say anything about fraction, so I'm going to title this mass. Okay. I'm going to number my half-life column. Always starts at 0. For this problem, I know that 2 half-lives went by. So they're telling me that 2 grams remained after 8 days. So 2 grams is down here. This is different in that I need to work my way back up. So to go down my chart, I cut in half. How do I work my way back up? I want to double. So 2 grams came from 4 grams. 4 grams must have come from 8 grams. So that was the mass of my original sample. Okay. Finally, guys, you can have them ask you what something's half-life is. Typically, this is not something on table N because otherwise you would just be able to go look that up, right? So let's see what they do give us. They're telling me that I started with this much and ended with this much. So let's set up a chart. Half-life, mass. If I know I started with 250 grams, can I figure out how long it took me to get to 31.25 grams? Absolutely. At time 0, that's how much I have. If I cut this in half once, I'm down to 125. If I cut it in half again, I'm down to 62.5. If I cut it in half one more time, here's my 31.525. So I can figure out that 3 half-lives went by. I also know that those 3 half-lives took 7 days. So can I figure out what 1 half-life took if I know that 3 takes 7 days? Absolutely. I'm working backwards here. It took me making my chart to figure out what I had to divide. So if I do 7 divided by 3, I know that 1 half-life took that many days. Okay. And I feel like that's a popular kind of question lately. All right. So what is all of this? What does this matter? I want to talk about how radioisotopes are useful and why their half-lives are important. As far as like medical uses go, guys, and I kind of mentioned this before, we want to make sure that our radioisotope has a short half-life because we want it to leave the body as quickly as possible. Okay, we don't want to be walking around radioactive. Okay, so this is just a chart, a very specific chart about what certain radioisotopes are used for in medicine. As far as like the reagents goes, these are your 2 important ones, your iodine and your TC99, what they're used for. I'm also going to add this to the bottom, cobalt-60. This radioisotope is very effective in cancer treatment. Okay. And it's kind of like the risk outweighs the usefulness has to outweigh the risk as far as using these radioisotopes go, because too much radiation can actually cause cancer. But if you're using that radioisotope for a very specific reason and it's targeted to a very specific part of your body and the rest of your body is protected from it and it leaves your body quickly, they can be very helpful. Other uses of radioactivity. So gamma radiation is used in food sterilization. That's pretty cool. Could kill bacteria. Carbon-14, guys, that's used to date once living things. So we can use half-life to figure out how old a fossil is, depending on how much carbon-14 is left in it. Uranium-238 is used to date rocks or geological features. If you look on table N, guys, carbon and uranium have very long half-lives. And that's good because we're dating things that are very old. So we need something that's going to linger around for us to be able to figure out how old something is. If it had a very short half-life, it would have been gone years ago, and we would never know how old these things are. Certain particles are also helpful to measure thickness. So, like, I don't know if you guys remember, we did the aluminum foil lab in the beginning of the year. Clearly, using a ruler is not a good way of deciding how thick a piece of aluminum foil is. But you can actually shoot particles through or at materials, and you can measure the amount of particles that pass through, and that could give us a very accurate idea of how thick something is that can't be measured with a tool that we have. So that's pretty cool. It's crazy if you look back in time before we really knew about radioactivity. A lot of these radioisotopes were pretty. So in the 1920s, they had glow in the dark watches that were highly radioactive. Clearly, we know now that that was not a good use. Um, Even if you think back to like just within like our parents' time, paint that was used in houses had lead in it, which we know now lead is one of those elements that has radioactive isotopes, and we should definitely not just like have that laying around. Um, Radon is just something that's around, especially if you have a basement. Um, Radon exposure is something you want to think about. It can cause cancer in non-smokers, and this is just a picture of the radon that's out there in the United States. It's just there. There's nothing we can really do about it. All right. And this is a picture. This is a picture of that when we talked about fission and we talked about how its radioactive waste needed a place to be stored. So this is where we take that radioactive waste and we put it, we like bury it in this mountain. So that's just pretty cool to see. I did mention, guys, that we would talk about accidents as well. So as far as nuclear power plants being safe, when there are accidents, they're horrifying. So these are just like the two big meltdowns that you've probably heard of in Chernobyl and in Fukushima. There was one in Pennsylvania. I think it was in the 1970s here. And it just like it kills these areas and it makes these areas radioactive. And the people that live in those areas and the environment, the wildlife, for years, cancers and mutations are showing up. Okay, so we'll definitely talk more about accidents in class, and I have a video if we have time that I could show you too if you're interested in this. Um, so it's like, the risk is the risk worse than the energy that we get? Like, which side are you on? What do you think is worse? This is a picture of a sarcophagus. Basically, in Chernobyl in Russia, they built this steel and concrete building over the reactor that melted down in the Chernobyl accident. And this is supposed to keep the radiation inside. Even those particles that have very high penetrating power hopefully cannot get through these steel and concrete walls. And finally, guys, just another, thing to talk about. As far as nuclear power goes, we also have to worry about nuclear weapons. Okay, so just talking about diplomacy, we have the Iran nuclear deal. We have deals with North Korea. Hoping that you know we're not we're not obtaining, or other countries are not obtaining, nuclear weapons, or creating a large amount of enriched uranium and plutonium to one day make nuclear weapons. Okay, so we're kind of all just agreeing to back off on that, putting limits on other countries, and hoping to all get along. because it could be used for something bad as well. All right, so that is it with our nuclear chemistry. I hope it's kind of interesting. So if you guys want to talk about anything when we get to class, sounds good to me.